Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Cauchy's theorem part 1 under the paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. As a prelude to complex integrations, rectifiable arcs and contours are defined. Complex integration is introduced. Integration along a regular arc and absolute value of a complex integral are described. Cauchy's theorem is stated and elementary proof of Cauchy's theorem is given. Deformation of contours is introduced. Cauchy's integral formula is derived. Using Cauchy's integral formula, derivatives of analytic functions and Cauchy's inequalities are obtained and Lovelace's theorem stated. The converse of Cauchy's theorem, that is Morera's theorem, is proved. So let us start with rectifiable arcs. Integration is one of the central ideas in the study of analytic functions of a complex variable. Cauchy's theorem is the most important result in this context and is the basis of many of its applications, particularly practical application in the realm of physics and geometry. But before discussing the theorem, it is useful to introduce the ideas of rectifiable arcs, contours and Riemann integration for a proper understanding of the condition under which the theorem applies. We first consider briefly how the length of a curve in the complex plane over which integration is to be performed can be defined. So let the equation of a Jordan arc be given in terms of a parameter t, so that z of t is equals to x of t plus iota times y of t, with limits t naught less than t, which is less than equals to t dash. So let z naught, z1 and zn be points on the arc corresponding to the parametric values t naught, t1 up to tn, which is equals to t dash. The length of the arc obtained by joining the points z naught, z1, z1, z2 and so on up to zn minus 1 to zn by a straight line, and it is L equals to summation I equals to 1 to n mod of zi minus zi minus 1. If L tends to a unique limit L as n tends to infinity, the greatest of the numbers mod ti minus 1 tends to 0. Then the arc is said to be rectifiable and L is called its length. The necessary and sufficient condition for a Jordan arc to be rectifiable is that the sum L should be bounded for all possible subdivisions of the parameter in the given range. We are concerned with regular arcs, arcs that have continuous tangents. For such arcs, the derivatives exist and are continuous in the entire range of the parameter t. And L is equals to integral from t naught to t dash under root of x dot square plus y dot square into dt. Now let us start with contours. If PQ and QR are two rectifiable arcs of length L1 and L2 which only have the point Q in common, then apparently the arc PQR is rectifiable and its length is L1 plus L2. From this it follows that a Jordan arc consists of a finite number of rectifiable arcs is rectifiable and that its length is the sum of length of its various sections. Such an arc is called a contour. A simply closed Jordan curve which consists of a finite number of regular arcs is called closed contour. A closed contour is obviously rectifiable. Now let us see the integration. In its application to physics, it is definite integral which is of greater importance. In the theory of functions of a complex variable, we begin integration as the limit of a sum over a certain path and later on find its connection to differentiation. Now consider a function fz of a complex variable z. For this purpose, we do not demand the function but only single valued at every point of a rectifiable arc. So let the equation of this arc be z as a function of t is equals to x function of t plus iota y function of t, where limits are t naught less than equals to t less than equals to t dash. Divide this arc into n smaller arcs by the points z0, z1 up to zn or z dash. The corresponding values of the parameters t are t0, t1 up to tn or t dash. Let summation be equals to summation of I equals to 1 to n of f function of xi I into zi minus zi minus 1 with limits zi less than equals to xi less than equals to zi plus 1. If this summation tends to a equal limit L is equals to n tends to infinity and the largest of the quantities ti minus ti minus 1 tends to 0. Essentially, it means that all interval tends to 0. Then we say that fz is integrable from z0 to z dash along the given arc L, and we write I is equals to integral along L of fz dz. In particular, if the length L is along the real axis, this reduces to the ordinary definition of the integral of a real variable. The points z0 and z dash then play the role of two limits of integration in the case of real variables. There is an important difference between the two cases. In the case of real variable, the result depends only on two limits. In the present case, the result in general depends on the path chosen between the two endpoints as well. That is why we write the integral L fz dz and not as integral z0 to z dash fz dz. Let us see an example and try to find out the integral L of z dz along any rectifiable arc joining the points z0 to z dash. According to the definition, summation equals to summation I equals to 1 to n of xi I as function of zi minus 1. Since xi is a point of rectifiable arc between zi and zi minus 1 and in the limit this interval approaches 0. This is the same as the limits summation 1 equals to summation I equals to 1 to n zi into zi minus 1 and summation 2 equals to summation I equals to 1 to n zi minus 1 into zi minus 1, or half of summation 1 plus summation 2 equals to half of summation I equals to 1 to n of zi square minus zi minus 1 square, which is equals to half of z dash square minus z naught square. Hence, integral along L of z dz equals to half of z dash square minus z naught square, which is independent of the path. Now let us see the integration along a regular arc. Let fz be a continuous along a regular arc L whose equation is given as z equals to x as function of t plus I y as a function of t with limits t naught less than equals to t less than equals to t dash. Then it can be shown that the function fz is interchangeable along L and the integral is I equals to integral along L fz dz equals to integral from t naught to t dash of f as function of t into x dot t plus iota y dot t dt, where ft is equals to f zt equals to f xt plus iota yt. This result is not only of importance as an existence theorem but also provides a practical method of finding integrals of complex functions by reducing them to integration of two real functions of a real variable. It can be shown that if fz is continuous on a contour L, then it is integrable along L. The value of the integral equals the sum of the integrals of fz along the regular arcs of which the contour L is composed. Let us see one more example where integral along L of 1 divided by z minus r dz, where L is the circle of radius r with center at z equals to r. So the parametric equation of L is z equals to r plus capital R cos theta plus iota capital R sin theta, with limits 0 less than equals to theta less than equals to 2 pi. This implies that integral along L of 1 divided by z minus r dz equals to integral from 0 to 2 pi of minus capital R sin theta plus iota capital R cos theta divided by capital R cos theta plus iota into capital R sin theta d theta equals to integral from 0 to 2 pi iota d theta equals to 2 pi I. So for second example, I is equals to integral gamma mod of z square dz, where gamma is the circle mod of z minus 1 equals to 2 traversed anticlockwise. The parametric equation of the circle mod of z minus 1 is equals to 2 is gamma as function of theta equals to 1 plus 2 e raised to power iota theta equals to 1 plus 2 cos theta plus 2 iota sin theta, with limits 0 less than equals to theta less than equals to 2 pi. Gamma dash as function of theta equals to minus 2 sin theta plus 2 iota cos theta, and mod of gamma as function of theta square is equals to 1 plus 2 cos theta whole square plus 4 sin square theta is equals to 5 plus 4 cos theta. So d theta equals to minus 2 sin theta plus 2 iota cos theta whole into d theta. Hence I is equals to integral along gamma of mod of z square dz is equals to integral from 0 to 2 pi of 5 plus 4 cos theta into 2 minus sin theta plus 2 iota cos theta whole into d theta, which is equals to 8 iota pi. Absolute value of a complex integral. If a function fz is continuous on a contour L of length L and on the contour mod of fz less than equals to n, then mod of integral along L of fz dz should be less than equals to nl. So proof of it: if the contour L consists of a sum of regular arcs, then the result for the contour can be obtained by adding the result for each regular arc and using the triangle inequality. Hence, we assume from the outset that the contour L is a regular arc. If g as function of t is any complex continuous function of a real variable t, then from triangle inequality, mod of summation I equals to 1 to n g ti into ti minus 1 less than equals to summation I equals to 1 to n mod of g ti into ti minus 1. On proceeding to the limit n tending to infinity and the largest of the quantities ti minus 1 tending to 0, we have mod of integral t naught to t dash gt dt less than equals to integral t naught to t dash of mod of gt dt. Let ft is equals to fzt on L, then mod of ft should be less than equals to n on L. Hence, mod of integral along L of fz dz is equals to mod of integral along L of ft into x dot plus iota y dot dt, which is less than equals to integral t naught to t dash mod of ft into under root of x dot square plus y dot square into dt less than equals to n times of integral t naught to t dash under root of x dot square plus y dot square dt, which is equals to nl. Since integral t naught to t dash under root of x dot square plus y dot square dt is equals to L. So what is Cauchy's theorem? Cauchy's theorem is perhaps the most important result in the study of complex analysis. We have remarked above that in general the result of complex integration depends not only on the endpoints but also on the path chosen between the two endpoints. Cauchy's theorem delineates the condition under which the integral is independent of the path chosen. It says that if fz is an analytic function regular in some domain D of the complex plane, z0 and z1 are the 2 points of D and L as rectifiable arc joining the 2 points that lie wholly in D. Then the integral of fz is independent of the path chosen and depends only on the points z0 and z1. This is a fundamental property of the analytic functions and may as well be regarded as the definition of analyticity. So Cauchy's theorem is usually stated in the following equivalent form. If C is a simple closest rectifiable arc lying in D, then the integral of an analytic function fz around C is 0. Any 2 points on C divide it into 2 rectifiable arcs, say L1 and L2. Let L2 bar be the arc L2 defined in the opposite direction. L1 and L2 bar are the 2 arcs joining the 2 points so that the integral is the same along these 2 arcs. Hence, integral along closed path C fz dz equals to integral along L1 fz dz plus integral along L2 fz dz equals to integral along L1 fz dz minus integral along L2 bar fz dz equals to 0. Now students, let us see the elementary proof of Cauchy's theorem. It is very difficult to prove Cauchy's theorem in its completely general form stated above. In the first proof, Cauchy made the additional assumption that the derivative f dash z is continuous within and on the contour C. Let D be the closed domain which consists of all points within and on the closed contour C separating z and fz into their real and imaginary part. So we write z is equals to x plus iota y and fz equals to u plus iota v. So integral along C fz dz is equals to integral along C u plus iota v into dx plus iota dy, which is equals to integral along C u dx minus v dy plus iota integral along C v dx plus u dy, which is further equals to integral along C ux dot minus vy dot into dt plus iota integral along C vx dot plus uy dot into dt. Now use Green's theorem. Integral C p dx plus q dy equals to double integral along d del q by del x minus del p by del y into dx dy. All the conditions for validity of Green's theorems are met. Hence, integral along C fz dz equals to integral along C u dx minus v dy plus iota integral along C v dx plus u dy, which is equals to minus of double integral along d del v by del x plus del u by del y into dx dy plus iota double integral along d del u by del x minus del v by del y into dx dy equals to 0. So by Cauchy-Riemann conditions, the conditions under which we have proved the theorem are sufficient but not necessary. It can be shown that if fz is an analytic function continuous within and on a simple closed rectifiable curve C, and if f dash z exists at each point within C, then integral along C fz dz equals to 0. Now what is deformation of contours? If a function is not regular within a closed contour, then of course its integral in general is not 0. The calculation of integral of an analytic function not necessarily regular around a closed contour is often simplified by deformation of contours. In this regard, we have the following theorems. First, the value of the contour integral of an analytic function is unaltered by any deformation of the contour, provided in doing so no singularities of the functions are crossed. Let us see its proof. Though the result is general, we shall prove it for special case in which one closed contour lies completely within the other closed contour. That is, if C1 and C2 are two closed contours, C2 lying completely inside C1, then that is, if C1 and C2 are two closed contours, C2 lying completely inside C1, then integral C1 fz dz equals to integral C2 fz dz. Now provided fz is continuous in the closed annulus and regular in the open annulus bounded by C1 and C2. Let us take 2 points A and B on C1 and C and D on C2 and join the two annuli as shown in the previous figures. Two loops L1 and L2 are formed. Sections AC and BD are common to both, but traverse in the opposite directions. Now fz is continuous in the closed domain and regular in the open domain bounded by L1 or L2. Hence, the Cauchy's theorem, its integral is 0 around L1 or L2. Integral along L1 fz dz equals to integral along L2 fz dz equals to 0, which implies that integral along L1 fz dz plus integral along L2 fz dz equals to 0. But since the arcs AC and BD are traversed twice but in opposite directions, their contributions cancel. The rest of the contour is C1 and minus C2. So hence integral along C1 fz dz minus integral along C2 fz dz equals to 0, which implies that integral along C1 fz dz equals to integral along C2 fz dz. Now we next discuss Cauchy's integral formula, which states that if fz is an analytic function regular within a closed contour C, continuous within and on C, and if A is any point within C, then f of A is equals to 1 divided by 2 pi I integral along C fz divided by z minus a dz. Now let us see its proof. Since fz is regular at A, so fz equals to fa plus z minus a into f dash a plus z minus a into eta, where eta tends to 0 as z tends to a. Hence, given any number epsilon, we can find a neighborhood mod of z minus a less than delta in which the inequality of mod eta less than epsilon holds. Now, draw a circle tau with center A and radius r, where r is less than delta and also so small that the circle tau lies entirely within the contour C. then Fz is regular in the annulus bounded by C and tau. Hence, by the theorem on deformation of contours, integral along C Fz divided by z minus a dz equals to integral along tau Fz divided by z minus a dz equals to f of a integral along tau 1 divided by z minus a dz plus f dash a integral along tau dz plus integral along tau eta dz, which is equals to 2 pi I f a plus 2 pi r f dash a plus integral along tau eta dz. This implies that mod of integral along C Fz divided by z minus a dz minus 2 pi I f a is equals to mod of integral along tau eta dz less than 2 pi r epsilon. The RHS tends to 0 as r tends to 0, but the left hand side is independent of r. Hence, mod of integral along C Fz divided by z minus a dz minus 2 pi I f a is equals to 0. This implies that 1 divided by 2 pi iota integral C Fz divided by z minus a dz equals to f of a. This formula expresses the value of the Fz at any point inside the closed contour in terms of its value at the points of its periphery. This is a real remarkable result, a consequence of the analyticity of the function. Example, I is equals to integral along C sin z divided by z square minus 6z plus 5 dz. The contour C is the circle mod of z equals to 4 traverse in the contour clockwise direction. Sin z divided by z square minus 6z plus 5 equals to sin z divided by z minus 1 into z minus 5 equals to sin z divided by z minus 5 whole divided by z minus 1. Fz equals to sin z divided by z minus 5 is analytic in the closed contour C. Hence, I is equals to integral along C sin z divided by z square minus 6z plus 5 dz equals to integral along C sin z divided by z minus 5 divided by z minus 1 dz equals to 2 pi iota sin 1 divided by 1 minus 5 equals to minus iota pi divided by 2 into sin 1. Now let us see the derivative of an analytic function. From Cauchy's integral theorem, we can easily find the derivative of the function at the point A, provided the interchange of operations of integration and differentiation can be justified. We will now show that the process is indeed justified under the same assumptions as were made of the proof of Cauchy's integral theorem. So, f dash a is equals to 1 divided by 2 pi iota into integral along C Fz divided by z minus a whole square dz. Let the shortest distance between A and the contour C be 2 delta. If z is any arbitrary point of C, then mod of z minus a is greater than equals to 2 delta. If mod of h is less than equals to delta, the point A plus h lies within C and its distance from C is not less than delta. On using the Cauchy's integral formula for f of a plus h and f of a, we have f of a plus h minus f of a divided by h equals to 1 divided by 2 pi iota h integral along C Fz into 1 divided by z minus a minus h minus 1 divided by z minus a into dz equals to 1 divided by 2 pi iota integral along C Fz into 1 divided by z minus a minus h into z minus a into dz. This implies that f of a plus h minus f of a divided by h minus 1 divided by 2 pi integral along C Fz divided by z minus a whole square dz equals to 1 divided by 2 pi iota integral along C Fz whole into 1 divided by z minus a minus h into z minus a minus 1 divided by z minus a whole square into dz. which is further equals to h divided by 2 pi iota integral along c fz into 1 divided by z minus a minus h into z minus a whole square dz. In the limit h tending to 0, the last expression also tends to 0 provided the integral mod of integral c fz into 1 divided by z minus a minus h into z minus a whole square dz is bounded. Mod of fz is less than equals to n, mod of z minus a greater than equals to 2 delta, and mod of z minus a minus h is greater than equals to delta, then mod of fz into 1 divided by z minus a minus h into z minus a whole square is less than equals to n divided by 4 delta cube. If the length of the contour C is L, then mod of integral along C fz into 1 divided by z minus a minus h into z minus a whole square dz is less than equals to n into L divided by 4 delta cube. The integral is therefore bounded, and this leads to the required result. F dash a is equals to limit h tends to 0 f of a plus h minus f of a divided by h equals to 1 divided by 2 pi I integral along c fz divided by z minus a square dz. Now let us see the higher order derivatives. The results we have just proved above, existence of the derivative of a regular function is truly remarkable. It follows from this that the function f dash z is itself regular within C. By obvious generalization, it follows that if fz is regular inside a closed contour C, derivatives of all orders of fz exist within C. Formally, f double dash a is equals to 1 divided by pi I into integral C fz divided by z minus a whole cube dz. Now to prove analyticity of f dash, consider f dash a plus h minus f dash a divided by h minus f double dash a minus 1 divided by pi iota into integral C fz divided by z minus a whole cube dz equals to 1 divided by 2 pi iota h into integral along C fz divided by z minus a minus h whole square dz minus 1 divided by 2 pi iota into integral along C fz divided by z minus a whole square dz minus integral along C 2 into h into fz divided by z minus a whole cube dz is equals to h divided by 2 pi iota into integral C fz into 3z minus a minus 2h divided by z minus a minus h whole square into z minus a into whole cube dz. By arguments similar to the previous case, it follows that the RHS is 0, hence f double dash a is equals to limit h tends to 0 f dash a plus h minus f dash a divided by h equals to 1 divided by pi iota into integral C fz divided by z minus a whole cube dz. The generalization to higher orders is obvious. If fz is analytic function regular within a closed contour C and continuous on and within C, it possesses derivative of all orders which are regular within C, and the nth derivative is given by f n times a is equals to n factorial divided by 2 pi iota into integral along C fz divided by z minus a raised to power n plus 1 into dz. So now let us solve an example where integral C cos z divided by z plus 1 raised to power 6 dz, where C is the circle of radius 4 with center at the origin. Here fz is equals to cos z and a is equals to minus 1 and n equals to 5. So this implies that integral along C cos z divided by z plus 1 raised to power 6 dz equals to 2 pi iota divided by 5 factorial into f raised to power 5 cos minus 1 is equals to minus pi iota by 60 sin 1. Cauchy's inequality. Follow immediately from formula for the derivatives of a regular function. Let the contour C be the circle of radius r centered at A. Let n be the maximum of mod of fz on C and mod of fz less than equals to n. Then on C, fz divided by z minus a raised to power n plus 1 less than equals to n divided by r raised to power n plus 1. The length of the contour is 2 pi r. Hence, f n a is equals to n factorial divided by 2 pi iota into integral c fz divided by z minus a raised to power n plus 1 dz. This implies that mod of f n a less than equals to n into n factorial divided by r raised to power n. This is the Cauchy's inequality. Now students, let us see about the Liouville's theorem. An analytic function which is regular in every finite domain of the z-plane is called an entire function or the integral function. Liouville's theorem states that if an entire function satisfies the inequality, that is, mod of fz is less than equals to capital N for all values of z and capital N being a constant, then fz is a constant. In other words, an entire function is either not bounded or is a constant. The theorem follows almost immediately from Cauchy's inequality for the derivatives of an analytic function. Since fz is an entire function and a is any point in the z-plane, fz is regular for mod of z minus a less than equals to r. Whatever r may be, it also satisfies the inequality. Mod of f dash a is less than equals to n by r. Now let r go to infinity. It follows that f dash a is equals to 0. Since the point a is arbitrary, the derivative of fz vanishes everywhere. So fz is constant. The converse of Cauchy's theorem or Morera's theorem. Let fz be a single valued function continuous within a closed contour C. The necessary and sufficient condition that the integral of fz along any contour within C may depend only on the endpoint is that fz be an analytic function regular within C. So, let us see the proof of it. The sufficiency of the condition is straightforward. To show that the condition is necessary, consider the integral of fz along a path from a fixed point A to a variable point z. Since by assumption the integral of fz is independent of the path, it is a single valued function of z. Denoted this function by gz is equals to integral from a to z fz dz. Let a be any point within C and let the shortest distance of B from C be delta. Then every point z for which mod of z minus a less than equals to delta by 2 certainly lies within C. Hence, if mod of h is less than equals to delta by 2, g a plus h minus ga is equals to integral from a to a plus h fz dz. Take the path of integration to be a straight line from a to a plus h. So 1 divided by h integral a to a plus h fa dz is equals to fa, which implies that g of a plus h minus g of a divided by h minus f of a is equals to 1 divided by h into integral from a to a plus h into fz minus fa into dz. Now by our assumption fz is continuous at a, so given an arbitrary number epsilon, we can choose a positive number eta depending on epsilon such that mod of fz minus fa less than epsilon for mod of z minus a less than eta. On using the result, mod of integral along L fz dz less than equals to nl, about the absolute value of an integral we get g of a plus h minus g of a whole divided by h minus f of a less than epsilon. provided mod of h is less than eta. Therefore, g dash a exists and equals fa. Since a was an arbitrary point, it follows that gz is regular inside C and its derivative is fz. Hence, fz is itself regular within C. This is often called Morera's theorem and usually stated as if fz is continuous and single-valued within a closed contour C and if integral along gamma fz dz is equals to 0 for every closed contour within C, then fz is an analytic function regular within C. In the process, we have proved the following important result. If fz is regular within a closed contour C, the integral from a to z fz dz taken along any closed contour in C is an analytic function regular within C has derivative fz. This is the fundamental theorem of the calculus of analytic function. It asserts that integration and differentiation are inverse operations. So students, now let us summarize what we have learnt in this module. As a prelude to complex integration, we begin with the definition of rectifiable arcs and contours. We next introduced the integration of a function of a complex variable, described integration along a regular arc, and obtained an inequality about absolute value of a complex integral. We stated and provided an elementary proof of Cauchy's theorem, which is one of the most important results in complex analysis. We then introduced deformation of contours and see how it helps in evaluating the integrals. Then we derived Cauchy's integral formula, which is of the great practical importance. Next, we used this Cauchy's integral formula to find derivatives of analytic functions and obtained Cauchy's inequality. We also proved Lovely's theorem about entire functions. Finally, we proved the converse of Cauchy's theorem, which is often called as Morera's theorem. Thank you.